Hi guys, this is a video about vector projections and where all those formulas about vector projections come from. First, where we left off in class was here. We have some vector A and some vector B, and they're anchored at the same initial point. And the projection of B onto A is this pink vector right here. Note that it is like the shadow of B onto A, and it also is created by dropping a perpendicular from the terminal point of B down to A, and we have a right triangle here. So the first chore is to figure out what the length of this projection vector is, and we use this thing called the component of B along A to figure that out. Let's talk about that for a moment. This is how it's written in the text, and it signifies the signed magnitude of this projection vector. Let's talk about the formula for it. How could you possibly find the length of this? Well, we can exploit the fact that this is a right triangle right here and write the length of this side in the following way. We know that cosine of theta is going to be adjacent, or the length of the red vector, over hypotenuse, which is the vector B. And so to find the length of this side, we just multiply cosine of theta by the length of the vector B. Now, why did I say that it was the signed magnitude of this vector? Well, remember that the angle between two vectors is not guaranteed to be less than pi over 2 or less than 90 degrees. What if we had a situation like this? Here, A and B have an angle theta that's greater than pi over 2 but less than pi between them. So what does the vector projection of B onto A look like? It looks just like that. It's the component of B that is pointing in the direction of A, but note that the size of the angle theta is now going to give us a negative value for cosine theta. So what does this mean? The scalar component is going to be the signed magnitude of the length. That means that it will give us the length of the vector, but if it's a positive length, that means that they're generally pointing in the same direction as in our first example up here. But if it is a negative number, that means the magnitude is the length, the sign is indicating that they're pointing in opposite directions. All right, let's return to our first example and talk about how to rewrite this using the dot product. Well, first thing is that we see that this is very, very close to the recipe for the dot product. What was it again? In class, we said that the dot product can be written as this. Let's try to get that right-hand side to match what we have up here for the component of B along A. We'll divide by the length of A. So now I have two things that are equal to the length of B times cosine theta. One is the signed magnitude of the projection vector here, and the other is A dotted with B divided by the length of A. Well, if two things are equal to the same thing, that means they're also equal to each other, so the big takeaway can be rewritten as this: that the component of B along A, or the signed magnitude of this vector, remember, if it's positive, they're pointing in the same direction. If it's negative, they're pointing in opposite directions, is equal to the dot product of the two vectors divided by the length of A. All right, now to find a way to write this actual vector, not just its signed magnitude. Well, remember the two things that characterize a vector are magnitude and direction, and we already have magnitude here. So now we just need direction. Well, this is pointing in the same direction as A, so I want a vector that is pointing in the same direction as A, that is this length. So what we need is a vector that is length 1 in the direction of A, and then all we have to do is multiply that vector by this scalar to give it the correct length. Well, now I need a unit vector, which is a vector that is length 1 pointing in the direction of A. The way to calculate that easily is to take A and divide it by its magnitude. Now, a lot of people don't believe me, but just for a moment, think about this. The length down here is a scalar, so this vector is really equal to this. And if you go through all the steps and use the formula to find the magnitude of a vector, you'll find that by dividing each component by the length of A, what you're essentially doing is dividing out the length. So you are left with a length 1 vector. I encourage you to do all the steps out on your own if you are still skeptical that this is a unit vector. But anyway, we have our unit vector here in the direction of A, written very succinctly this way. So all we have to do is multiply it by this scalar. Our result will be a vector in the appropriate direction. Note that the scalar will control correctly whether to point this vector in the direction of A or opposite direction as A. So let's take a look. There's our formula for how to write this red vector, this red projection of B onto A. This first term is identical to the component of B along A. It is the signed magnitude. It controls the length as well as the direction, whether it should be in the exact same direction or the exact opposite direction as A. And then this is just a unit vector in the direction of A. So note that the component of B along A is the signed magnitude. It is a scalar. Whereas this guy up here, that's the actual vector in pink. Hope that clears up things, and if you have any questions, please let me know.